Section 4.3, we're going to explore our number system a little bit more and a little bit of the history and how we've developed some of the things that we have. So this is arithmetic in the Hindu-Arabic system. Remember, that's our number system. So for starters, we're going to talk about expanded form. We've looked at expanded form in other bases. This is a form in which the value of each digit in its position is made clear. So in other words, instead of thinking the number 942 as 942, we think of it as 9 hundreds, 4 tens, and 2 ones. Okay, so we looked at expanded form when we were writing down like the Mayans just a little bit ago, and when we would write them as a number times 143,000 plus a number times 7,200 plus a number times, that's expanded form for Mayans. So we're looking in this section at our expanded form. So when we think about this number 12,398, what it means is we take each value, each digit, and we write its place value next to it. This 1 is in the what's place? The 10,000's place. So we write 1 times 10,000. The 2 is in the what's place? Thousands place. So it's 2,000, but it's in the thousands place, right? The 3, the hundreds place. The 9, the tens place, and it's not a 1, is it? It's an 8. The 8 is in the ones place. Okay, so there's another form of this that you need to be aware of, but this is what we're talking about. This is expanded form in its sort of written out version. Each of these numbers that we're multiplying by, the 10,000, the 1,000, the 100, the 10, and the 1, are all what are called powers of 10. Okay, so I'll do it with the 9 first. This is 10 to the 1. Right, 10 is 10 to the 1. And probably the 100 you can understand pretty okay, like obviousness. It's 10 squared. Right, that's what 100 is. It's 10 times 10. We can do this with all the values. Do you know what the 1,000 is? It's 10 to the third. What about 10,000? 10 to the fourth. And there's several sort of ways, I'll get to the one at the end in a minute, but there's several ways that you can remember how to do that. If they're all represented by numbers, like we have a number in every place value, if you can just find the 10, you can just work your way up like we did, right? It goes the first place, the second place, the power of 3, the power of 4, and so on. We can do that. Another way that you can look at it is look at the power and look at how many zeros are in the number. 10,000 is 10 to the fourth. How many zeros are in 10,000? 4. That power is actually representative of the number of zeros that are present. The power of 4 means I have 4 zeros, right? The power of 2 means that I have 2 zeros, the number 100. Now, the one at the end, does anybody know how we represent the number 1 as 10 to a power? It's 10 to the 0. You can think of it in terms of patterns, right? We went from 10 to the first, and then we went to the second, and we went to the third, all the way when we went to the left. If we go to the right, we go down a power. Going down from 1 would be 0. That's one way to recognize it. You can also recognize it as the number 1 is actually a 10 without a 0 at all. It's got 0 zeros, right? You know, if we have a power as 10 to the fourth, it has 4 zeros. 10 to the 0 would have 0 zeros. You can think of it that way. There's also a fact that you've probably learned in an algebra course somewhere that says anything to the 0 power is 1. So that's another thing you can do to remember that. So any of those are fine methods for sort of remembering how this works. Now, we also want to be able to take a number that's in this expanded form like this and to write it out properly. So one of the things that we need to make sure of when we do this is that we have all the powers present, right? So if it skips from 10 to the 5th down to 10 to the 2nd, we don't want to miss that changed drastically. We don't have a 10 to the 3rd, we don't have a 10 to the 4th. So on this one, I think we have them all, right? This is the 5, power 4, power 3, power 2, power 1, and power 0. If we have all the powers present, then we can actually take the number that's being multiplied by them in each case, and it simply becomes the number in that place value. So the 5 would be written first. The 0 is second, and then I have a 3, and then there's a 5, and then a 6, and then an 8. I'll put my comma in the appropriate place because that's one of our conventions that we use, right? To put that comma there. This is 503,568. And you should be able to check to make sure that it works. For example, this 5 to the 10th should be a 5 followed by 5 other place values. 1, 2, 3, 4, 5. It is. You can check it from that perspective too. Okay. You've seen this property before, maybe not written in this fashion. It's the distributive property. You usually see it written in an algebra course where this piece is on the left side, like the equation flops from what we normally see here. And somebody draws some arrows in like this. They say, look, I can draw the A through here. So this is A times B plus A times C. What this is actually showing is the reverse of that, which is fine. It's saying, hey, if you have an A in here, it's multiplied by two things, you could sort of pull it out afterwards and just add the B and the C together first. And this property holds for all real numbers. So it holds for fractions, it holds for decimals, it holds for radicals, and pi. It holds for everything. Now, we're using it with whole numbers, and specifically with positive whole numbers, but it holds for everything. So let me show you why it matters. We're taking a look at the numbers 75 and 34, and it wants us to add or subtract in expanded form. Now, obviously, number one, you know how to add and subtract this, probably in your head. If not in your head, you could write it on paper. And number two, you have a calculator that could do it for you. So there's no reason to miss the answer here. Agreed? But what will happen inside of my math lab is that it will expect you to show the work piece. Like it'll have you fill in the boxes for the work piece. So that's the piece I'm going to try to focus on with you, and it should match the answer that we expect it to be. What is 75 plus 34? What are we going to be getting as our answer when we're done? 109. Okay, so 109 is our expected answer, right? Okay, so just keep that in mind as we work. So here's how this goes. We're writing each of these numbers in expanded form. So this is 7 times 10 to the 1 plus 5 times 10 to the 0. Is everybody good with that? And we're going to add it like old school style, like you do back in first grade, where we put it on the bottom. So the other number, 34, is going to go directly underneath the 75. So it's 3 times 10 to the first plus 4 times 10 to the 0. Okay, everybody good? Okay, what we're doing is we're adding vertically, just like we've done before. Why am I allowed to add the 5 and the 4 together? Well, you've probably thought about this before, but maybe not so much because it just seems obvious, right? You're adding them together because they're in the same place value. Well, this is actually written in the place value next to it. The place values are 10 to the 0. The reason I can add these together is because of the distributive property. They're both multiplied by 10 to the 0. That's what allows me to add the 5 and the 4 together. Did you know that? It is. It's the distributive property there. So I can add straight down. I can say, okay, well, this is 9, 10 to the 0. I can do the same thing here. What is 7 plus 3? 10, which is 10 times 10 to the 1, and that's not a good thing. I mean, it's not a bad thing. But somehow I ended up with a 2-digit number here, right? And you know that you can't just end up with a 2-digit number and write it down, especially if the numbers had been longer, right? You'd have to do something like, we call it regrouping, or you might be thinking about it as carrying. Is that a phrase you've heard before? So what happens is when we get a two-digit number like this, you break it apart and you say, okay, well, this is the number 1, right, because it's the number 10. So I take the 1 of the 10 and I move it over. And now it's times 10 squared. And I leave the number 0. Right, so here's this number 1 got moved over here. This number 0 got moved over here. This is 0 times 10 to the 1. And then I still have my 9 times 10 to the 0. So the two-digit number gets separated. The bigger value moves over one place value. The smaller value stays there. Okay? And in the end, do you see the 109? They're there. Okay? And there will be like a scaffolding inside of my math lab where there'll be like blanks everywhere. And they'll have you fill in the blanks with these numbers. That's what they're going to have you do. They're going to have you fill in blanks to show that this addition is happening in a expanded form. So I want to show you a subtraction one next. So again, let's figure out what it is we're expecting. What is 74 minus 48? 26. So our answer at the end is going to be a 26. Okay, good deal. So we're going to write it out again. 7 times 10 to the first plus, sorry, was it 7? Yeah. 4 times 10 to the 0. And then we're going to subtract 4 times 10 to the first and 8 times 10 to the 0. You might notice for the moment I left a blank in between here. Right, I'm subtracting the number 48, but that means I'm subtracting the 40 and I'm subtracting the 8, so I'm actually going to write a negative here as well. I'm subtracting all of it, so I'm just subtracting both pieces. Now there's a problem that happens here. I can't take 8 away from 4. Not the way it's written, right? So what do you have to do when you take 8 away from 4? What do you do to make that happen? Yeah, you take one of the 10s away from the number 7. You borrow or you regroup. Literally think about what happens with money. If you took a $10 bill and you turned it into 10 $1 bills, that's what's happening here. So we take one of these guys and we add one over here. We add the 10 over here to give you 14. So again, what will it look like in my math lab? Well, it'll look like that they will decrease this by 1, and this will now say 6 times 10 to the 1. And it will say 14 times 10 to the 0. And then they'll have the other pieces written below. And now we can subtract. What's 14 minus 8? 6. So it's 6 10 to the zeros. And what's 6 minus 4? 2 times 10 to the 1. And of course, you see the number 26 showing up right here as expected as well, right? Okay. Have you ever heard of an abacus? Oops, I'm sorry. A couple people still writing, I apologize. You good? All right. Everybody else good? Not yet. Okay, sorry. I'm in a let's get it done, move fast mood today. Sorry about that. Okay, everybody good now? Okay, let's try again. Have you ever heard of an abacus? Probably in some like olden form of something. Somebody mentions the word abacus. Maybe you've never seen one used before. So we're going to talk about one of the oldest calculators that exists for our system anyway, and that's the abacus. In the abacus, this was used for speed calculating. We're simply going to be looking at how numbers are represented on an abacus. That's what we're going to be focusing on. The beads that are pushed toward the middle are active. The others are ignored. We'll come back to that in a little bit. Beads above that middle rod are worth 5, kind of like the Mayans. Beads below the middle line are worth 1. And each of the vertical rods is a power of 10. So we have 10 to the 0, 10 to the 1, all the way to 10 to the 5 on a, 10 to the 4, on a typical abacus. Okay, so here's a couple things that I want you to remember as we look at these. The dots are color-coded for our benefit. They're not really changing colors, okay? So there's blue and there's black dots on your beads. That's what they're beads. They slide along these rods. But they're not really blue and black. They're all the same color. They're just showing them in different colors to try to draw your attention to what's going on. So the beads in the middle, the ones that they're showing in black, are considered active beads. They contribute to the number that we're trying to describe, okay? These other blue beads are simply there because this is a physical object and we're not taking the beads on and off the rods. Does that make sense? So imagine this bottom line and this top line are pieces of wood or metal. They're binding those beads there. You can't just remove the beads, right? So what do we do if we don't want to use them? We just push them away. We either push them up or we push them down away from the middle rod. Does that make sense? You can see the powers of 10 listed below. So this is the 10 to the zeros place. And we have a 10 to the ones place, all the way to 10 to the 4, just like we wrote down the numbers when we were writing expanded form. And we can actually write this number down. So I will write the number below what it seems to be. So this one right here, this 10 to the 0, I have a bead from the top pushed down. The beads from the top are worth 5. And I have a bead from the bottom pushed up. So I have a 5 and a 1. This is a 6. Do you see where I got 6? Okay. What would this next one be? It's 0. There's no beads near the middle. So this is the number 0. How about my next one? That one's 7. The next one is a 1. And my final one on the left-hand side is a 3. So this is the abacus representation for the number 31,706. That's how we would represent it on this abacus. Okay? All right, so we're going to do another one. I've got the picture, but you don't, so you're going to have to draw it in just like the last time. So go ahead and sketch this picture. After you've sketched it, well, notice, there's no powers of 10 written underneath it, right? That's not part of the picture. It was on my example, but it's not part of the picture, not a part of the abacus. Go ahead, after you have drawn it in, write the number that you believe for it to be, and check with a neighbor. See if you get the same thing. Okay, so you're looking around, find somebody who's finished, see if you can check that yours and theirs arrive at the same result.
So the blue is like, they don't count, they're just there.
Right. They're trying to help you out by color coding them. In a real abacus, they wouldn't be color coded, but the blue ones are showing the pushed away non-counting beads is the way that they're drawing them in the pictures you're seeing.
So the ones that you need to count are just the round ones.
Yeah.
The
What number did you guys get?
10,256.
10,256. Okay, are there any of those digits that are concerning or that you didn't quite see why they were? Yeah, I can. So this black dot right here, being below the line, would equal a 1. The next one has no dots that are black. They're all blue, so that's a 0. The next one has 2 black dots pushed up toward the line, so that's the number 2. The next one has 1 black dot, but it's above the line. Above the line dots are worth 5. And then on the last one, I have 1 above and 1 below, giving me a 6.
So
Okay.
above it is 5 is below this.
Correct. Yeah, and what it is it's a way to minimize having to need so many beads, right? I mean, could you have had 9 beads on each strand and done it that way? Well, yeah, but you'd need more physical beads to do that, right? By doing it this way, I don't need 9 beads on a single strand. I only need 5. Yeah? Think about making something that's like this. It'd be cheaper to make, wouldn't it? Yeah, it would. Fewer beads. Okay, what we're going to do next is we're going to actually sketch an abacus that has the properties that are listed. So go ahead and draw something in like you have been. And I'll draw one as well.
Can we just sketch the part that's like active?
So to answer your question, in reality, they would, I mean, you can for what you're doing because you're not turning anything in written form in. Does that make sense? But when you look at this and you compare it with what's on my math lab, the beads are going to be there whether you want them there or not. I think I like it that way. That probably worked. Okay? So I'm going to draw mine in because I know that's what my math lab's going to show you. But if you wanted to leave yours off for the time being, you could do that. Just recognize that they're still going to be there when you get inside that environment. Okay. So we have the number, I think I've got a number, 1, 2, 3, 4, 5. I think I've got enough lines. So we have the number 7. How do I get the number 7 to show up properly? Okay, I need 1 bead on the top and 2 beads on bottom. I'm trying to make my 1 on top, 2 on bottom. That's not too bad. They're a little bit fat. And then as promised, I'm going to draw my 2 missing beads that are on bottom. I'm going to make them a little thinner. I'm not going to have space. There we go. And then I have 2 beads on bottom. And I'm drawing them all in yellow because they really would all be the same color. My beads are not perfectly lined up, but they're okay. I think we're all right. That's 7. How do we get the number 0? Nothing. So nothing doesn't mean there's no beads. Like we don't physically take the beads off. It means they're pushed away. So the 1 bead on top is pushed up, and the 4 beads on bottom are pushed down. That's better. How do I get the number 1? 1 bead that's pushed up from the bottom. So the top bead's pushed away, and then the other 3 beads are pushed down. Something like that. 6. Right, 1 on top and 1 on bottom that are pushed toward the middle. And then I need 3 more of the on bottom pushed away. My beads are getting worse as they go. Okay, one more time. The last number is number 3. How do I get the number 3? 3 dots under the line. And then the 4th dot, 4th bead, would be pushed away. And the bead above would also be pushed away. All right. So we're going to do an interesting thing. And for those of you who are education majors, you'll see this again in another course. For those of you who hope plan will sometimes be a parent, you will probably see it come home in your child's homework at some point too. Just letting you know. So this is called lattice multiplication. for products. I'm going to show you how it works, but first we're going to just write down all the details of how it works. You create rows and columns for your digits. You divide each box along the diagonals. You compute each single digit product, recording the tens digit in the top left and the ones digit on the bottom right. That says ones, not is. And you add along the diagonal from right to left. So jot all those down, and then a picture will help. So we're going to do an example that shows these steps in action, and you can see how they all play out. The example we're going to do is the number 23 times the number 187. So here's what we're going to do. You can either write the 2 and the 3 on the top, or you can write the 187 on the top. I'm going to write 1, 8, and 7 on top. Okay, just write the number 187 so it's spread out a little bit. And then I'm going to draw a box underneath it. Let me do that next. The box needs to be longer than it is wide. The reason is because the number 187 is along the top, but I'm going to put the number 23 along the side over here, and it needs to be on the right-hand side. Do not put it on the left. And we're going to split our box into rows and columns. So I end up with a 3 by 2 box because I have a 3-digit number and a 2-digit number. If I had a 3-digit number and a 3-digit number, I'd have a 3 by 3 box, and so forth. Okay? It talks about splitting things along diagonals. It means this. I make a diagonal split along each of the 6 boxes that I have. And this is why it's called a lattice, is because it has the imagery of a lattice, like a diagram. So called lattice diagrams or lattice method. Now here's what we do. Each one of these boxes is going to have the product of the row and the column it's on. So the first one, I'm in column 1. I'm on row that's got the number 2 in it. So I do 1 times 2, and I get the number 2. And I'm going to write the number 2 in the bottom right-hand corner. Then I have the column that I'm on is 8. The row is still 2. 8 times 2 is 16. And I write the 1 in the top left-hand corner and the 6 in the bottom right-hand corner. So that's what it's talking about. It says the tens digit in the top left, ones digit in bottom right. So here's 16 like this. So next one I have is the 7 and the 2, which give me a 14. Now I have the 1s and the 3s. It's a 3, so I'm going to put it right here. I have the 8 and the 3, which is a 24. And then I have a 7 and a 3, which is a 21. Okay, so here's something that you have to understand about mathematics. There's usually lots of ways to do problems in math. I don't know if you've been taught that along the way, or if it's been my way or the highway with your teachers, but there's usually lots of ways to do problems. There's sometimes a preferable way, and sometimes there's not. But usually when a way is preferable, we tend to gravitate towards something being preferable because it works quickly, right? It's efficient. A lattice method's not very efficient. It's a lot of writing. It's a lot of drawing. It's not terribly efficient. But there's a couple of things that it has benefits of that our typical method for multiplication does not. One thing is you did all of the multiplication at one time. Think about what happens when you multiply these out with it's called a standard algorithm for multiplication. In the middle of the multiplication, you do addition. 3 times 7 is 21. You write the 1 here, you write the 2 here, and then you have to do 3 times 8, which is 24, and then you add a 2. Right? You're trying to do 2 operations at the same time. That makes things very difficult. Right? You get into the habit of it, you get the hang of it, and it becomes very efficient. But when you're first working with it, it's not terribly good. I have a daughter who's exceptional at math. She's actually getting a math minor right now. She could not understand for the life of her the standard algorithm for multiplication when she first learned it. And she's not dumb. It just didn't make any sense why she was doing addition in the middle of multiplication. That created a problem for her. Okay? And then what happens is then when you move on to the next one, so let's actually finish this first line of the standard algorithm. So I have 24, 26, I have a 2, 3, I have a 5. Then all of a sudden there's a mysterious 0 that shows up. It's really not mysterious, but it feels a little bit like hocus pocus when you first do it. You tell the kid just write a 0 there or skip a spot. Why? Well, the reason you do that is because what you're multiplying by next is not really 2, it's 20. And 20 has a 0 in the ones place. But I don't know about you, but none of my teachers ever told me that. I just knew I put a 0 there. It's efficient, but it's not really very effective in understanding what I did. Now, I'm not going to finish the problem, although you certainly could, right? You should be able to know the answer that we're about to get here, either by doing it with standard multiplication or your calculator. It's not a mystery. I want to go back to my lattice multiplication and show you how it finishes up. Okay, so what we do next is we extend these sort of diagonal lines down. And we add. So we've isolated the addition and we've isolated the multiplication. We did all the multiplication. And we add and we start with the bottom right-hand corner. Okay, we're only adding what I've done in yellow, or the ones you've written in the box. The values along the top, the 187 and 23, we're not adding those. Those were the values we multiplied with. We're only adding the values we've just created. I'll change colors even for the sake of this. I'll do it in orange. So this is the number 1 down here, because this column, or excuse me, this diagonal is a 1. My next diagonal is 4 plus 2 plus 4, which is 10. But within that, we have to write down the 1's digit, and we have to carry, or regroup, the 10's digit, the 1. So the 0 gets written down, the 1 gets written up here. And then we add this diagonal together. 1 plus 1 plus 6 plus 2 plus 3. What do we get? What'd you have? 13? It did carry the 1. I did it in orange up here. Oh, you mean for the next line? Yes, you're correct. So the number's 13. Yep, you're just moving ahead. So I put a 3 down here, and I regroup or carry the 1. And my last diagonal is 1 and 1 and 2, which is 3. 4. Sorry, 4. I zoom in and zoom out on my screen so much, and I lose values and things. So that's what happens. It's not because I can't add 1 and 2 and 1. I promise. Okay. So my number at the bottom here is 4301. Oh, good. That's what I have written down on my paper. That's good news. And could you check it with your calculator? Of course you could. Of course you could. So we're going to do another one. You ready? Okay. So we're going to do a 3 by 3 one. Right? 3 digits by 3 digits. Doesn't matter where you put the numbers. So I'm going to put my numbers as they're written on the top and the side. So I'm going to put the 9 and the 1 and the 2 over here. And then I have a 4 and an 8 and a 3. And I'll have a box. It's a 3 by 3 box. Something like that. And then I put my diagonals in. Okay, so we're going to multiply each box out. So I have 9 times 4 is 36. 1 times 4 is 4. 2 times 4 is 8. That's my first row. Now I have 9 times 8, which is 72. 1 times 8 is 1, and 2 times 8 is 16. 9 times 3 is 27. 1 times 3 is 3, and 2 times 3 is 6. We extend our diagonals. And we add values together. So this one's 6 in the bottom, right-hand corner. My next diagonal is 6 plus 3, which is 9. Then I have 8 plus 1 plus 8 plus 7. What is that? 24. Yes, it is. Thank you. Just 24. So I have 4, and I carry my 2. Then I have 2 plus 4 plus 2 plus 2. 10, which is a 0, and carry my 1. a 1, a 6, and a 7. 14. 4, carry my 1. And then 1 and 3 is 4. So my answer is this piece right here. So I have 440,496, or 440,496.